Good afternoon. Today we will be discussing our concept design for a multi-purpose fishing trawler named the Barramundi Atlantic. First, I will review the outline of our presentation. I will begin by introducing our group members, and then I will discuss our mission requirements and principal particulars. Next, Hendrix will showcase the arrangement of our vessel and describe our fish hold and refrigerated seawater system. Afterwards, Abby will explain the development of our hull form, our structural arrangement, and tonnage estimates. Lauren will conclude by describing our weights and centers, stability, vessel systems, and future design work. Before we begin, I would like to take a moment to thank Professor Golden and our industry mentors, Phil Essex, Luke Kiley, Brent Morrison, and Thomas Waters, for their guidance, contributions, and commitment to our vessel design. I will now introduce our design team. First, my name is Phoebe Garret, and I'm from Lake Oswego, Oregon. Next, I would like to introduce Lauren Kirk from Rochester, Massachusetts. Next, I would like to introduce Hendrix Lovett, who is from Wichita, Kansas. Finally, I would like to introduce Abigail Ng, who is from North Haledon, New Jersey. Now I will summarize all design objectives that our vessel must comply with to meet the owner's expectations. The vessel is to be a multi-purpose fishing trawler that will operate along the eastern seaboard of the United States. The vessel will work year-round and will specialize in trawling bottom fish, midwater fish, and shellfish, shifting to different fishing grounds throughout the different seasons. The vessel will be U.S. flagged. Our vessel's technical requirements are as follows. The maximum full load draft is 4 meters. The transit speed requirement is 11 knots, while the trawling speed requirement is 3.5 knots. The cargo capacity requirement is 500 cubic meters. The complement requirement is made up of 2 officers and 7 crew. Our vessel endurance is 20 days, and the gross tonnage of the vessel must be under 200 gross registered tons. An additional owner's requirement relates to the vessel's environmental impact. When compared to similarly fueled vessels of a similar size, we must demonstrate that this vessel is capable of a 25% reduction in the use of conventional fuels. Our solution for this design challenge was to integrate a biodiesel blend known as B20 into our main diesel engine. B20 is a renewable, non-toxic, clean-burning alternative fuel. B20 is a 20% biodiesel, 80% regular diesel mixture that can run through our diesel generators without any engine modifications. Biodiesel B20 has good cold weather performance, is the most accessible biodiesel currently on the market, and can be locally sourced. I will now discuss our vessel's regulatory requirements. Our trawler must comply with Class NK's rules for survey and construction of steel ships, IMO's intact stability code, and the life-saving appliances and firefighting systems in accordance with 46 CFR. The major vessel systems that required engineering attention during our design process include the following: our main propulsion system, our refrigerated seawater system, fuel oil, deck gear, freshwater systems, our superstructure and hotel loads, our life-saving and firefighting systems, and our waste systems. Finally, I will summarize the Barramundi Atlantic's principal particulars. Our length overall is 41.4 meters, and our length between perpendiculars is 36.4 meters. Our beam is 12 meters, our draft is 4 meters, our depth is 6 meters, and our cargo capacity is 533 cubic meters. Now I will hand over the presentation to Hendrix to discuss the general arrangement of our fishing trawler.
Thank you, Phoebe. I will now use our inboard profile to discuss our general arrangement plan. The fish holds are located about midship. In all operating conditions, they contain pressed refrigerated seawater that are capable of maintaining a catch temperature of 0 to 5 degrees Celsius. Our machinery space is located aft of the fish holds in both the lower and tank top decks. This is also where our primary powertrain is located, including the main engine, reduction gear, thrust bearing, and steering gear systems. Forward of the fish holds lies our auxiliary machinery space. This is where our raw water, potable water, freshwater cooling, and refrigerated seawater systems are located. Above the auxiliary machinery space is our accommodation block, comprised over the forward section of our forecastle deck, as well as our upper deck. This is where crew staterooms, stowage spaces, laundry facilities, and galley services are located. Near the aft main deck access point, the arrangement includes spaces for crew to store wet items such that they do not spread dirt and water throughout the living spaces. The pilot house is located above the accommodation block. Within this space, operators have access to the vessel's navigational and steering systems. Additionally, aft windows within the pilot house provide visual reference to all of the trawl equipment located on the main and upper decks. Control panels for these items are located near the aft bulkhead of this space. I will now use the upper deck and main deck plan views to discuss the vessel's onboard trawling procedure. By definition, stern trawling is a commercial method of fishing that involves the tow of large nets through the water column. Otter doors, commonly called trawl doors, act as supportive hydrofoils that facilitate shape changes in the trawl mouth. These alterations aid in mitigating the presence of unwanted fish known as bycatch. Trawling winches are the main point of connection with the vessel's deck equipment and the trawl itself, facilitating the distance between both item groups. Sounding winches aid in maintaining the trawl's depth for a certain fishing operation. And at the conclusion of the trawling period, a pair of forward Gilson winches are used to haul the trawl up a 27-degree incline until the cod end is positioned onto the non-slip trawl arena surface. The aft Gilson winch and cantilever gantry systems vertically reposition the cod end of the net, and they allow fish to spill from the net and onto the trawl arena. The fish are then hosed down and a final bycatch removal process is performed. At this point, each of our 4 hatches are opened and the catch is stored within the pressed refrigerated seawater holds. The trawl drums are used for storing the nets such that they are fully rigged for fishing operations. The aft net drum houses the primary trawl equipment, and the forward net drum houses the spare equipment. This allows for both pelagic and demersal trawling operations to occur in one voyage with minimal interchange time. Once the catch is stowed, the refrigerated seawater system preserves the cargo for the required 20-day endurance. Fish are maintained at a temperature of 0 to 5 degrees Celsius using our recirculated seawater from the port and starboard holds. The plant is comprised of an RSW unit, a condenser, a receiver, and an evaporator, with an ammonia refrigerant being used for the system. After the vessel has returned to its port, local fisheries offload fish using shore facilities such as portable eductor units. I will now pass the presentation off to Abby so that she may discuss our hull form.
Thank you, Hendrix. I will now discuss the development and hull form of the FV Barramundi, illustrated by our lines plan above. To develop the hull, several stations from our general arrangement were imported into Rhino to loft an initial hull surface. Following the initial hull form, various adjustments were made to better suit the mission of our vessel and meet typical hull characteristics observed in our parametric analysis. It was noted that fishing trawlers of similar sizes did not have chines, so it was omitted from this design. The hull was adjusted to have a slight shear by the bow, as typical of fishing trawlers. This shear increases our freeboard forward and limits the amount of water on deck, useful for operating in the North Atlantic. The initial hull form was adjusted to allow for greater space in the aft portion of our vessel. This accommodates for our aft machinery space, which includes main propulsion, steering, and electrical systems. The hull was altered to have a slight dead rise angle, giving it a V shape rather than a flat bottom. This allowed for exemptions of volume in our tonnage calculations by zeroing the bottom breadth. One major change to our hull form during the design process was a beam expansion from 10 meters to 12 meters. The greater beam better suited our vessel arrangement, improved our stability, and supported meeting our maximum 4 meters design draft. The FV Barramundi has a displacement hull with a block coefficient of approximately 0.6, a typical value of a fishing trawler. After developing our hull and Rhino, a geometry file was exported for use in hydrostatic analysis in GHS and powering analysis in NavCAD based on the UBC Trawler series. Next, I will discuss the structural arrangement of the vessel. The FV Barramundi has a steel structure and is transversely framed. Transverse framing is suitable for smaller vessels and is often easier to produce in areas of great curvature. Our frames are spaced 700 millimeters apart in accordance with Class NK requirements. The design section modulus exceeds our regulatory requirement to support our anticipated loads, the greatest of which on our structure are present during trawling when the large trawls are dragged through the water. In addition, loads due to the superstructure are supported by the continuity of bulkheads below the deckhouse. In addition to our typical engineering considerations, our team considered the gross register tonnage of the FV Barramundi Atlantic. Tonnage is a volume-based estimation of the cargo carrying capacity of a vessel and has several impacts on the manning and regulation. Optimizing the tonnage of a vessel has potential to save ship owners both time and money, but can have adverse impacts on construction and weight. For this design, we had a maximum requirement of 200 gross register tons. Vessels under 200 gross register tons do not require a master or licensed engineer on board and may be considered uninspected towing vessels. Given our requirement of 500 cubic meters of cargo space, our team took several steps to minimize tonnage contributions both above and below the deck. The underdeck tonnage of the vessel was minimized by use of deep framing techniques. In this, alternating transverse frames 1.4 meters apart were extended towards the centerline in cargo tanks and machinery spaces on the lower and tank top decks. Deep frames must be symmetrical and minimize the tonnage volume contribution by shortening the breadth used in calculations. The inclusion of deep frames increases the weight and material of the structure and may limit access to vessel spaces. Several lightning holes were used to minimize the adverse effects and improve area access. In addition, space excluded from tonnage by deep frames may still house machinery and crew areas. The underdeck tonnage contribution was estimated to be 193 gross register tons. Tonnage openings and a progression through the deckhouse were used to eliminate all major superstructure contributions to tonnage by considering them open space. Tonnage openings may not be watertight and affect the arrangement of the superstructure. Our vessel utilizes 4x5 foot and 3x7 foot openings in the superstructure, as well as pairs of 3x4 foot tonnage openings to create a progression through the forecastle deck. Areas including deckhouse machinery spaces, public water closets, and portions of the bridge are exempt from tonnage measurements. The superstructure tonnage contribution was estimated to be 3 tons. The gross register tonnage was estimated to be a total of 196 gross register tons, under our 200-ton limit. Now I will pass the presentation on to Lauren to discuss the weights and centers of our vessel.
Thank you, Abby. I will now discuss the vessel's weights and centers. The vessel's total weight was estimated to be 1,184 tons. This breaks down into a light ship weight of 539 tons and a dead weight of 645 tons. The light ship weight consists of the structural, outfitting, and machinery weight. The dead weight consists of our consumable loads, such as fuel oil and fresh water. The largest deadweight load by far was the cargo load, which weighs approximately 580 tons. A 10% acquisition margin was added to each weight component, and an overall service margin of 10% was applied to get our total weight estimate of 1,184 tons. The longitudinal center of gravity was estimated to be 17.3 meters forward of the AP, which falls just aft of our 17.4 meter LCB. This bodes well for stability. The KG was estimated to be 4.1 meters above the baseline. I will now discuss stability, starting with the 3 loading conditions we assessed to analyze stability. These conditions were light ship, full load departure, and full load arrival. In the light ship condition, all the deadweight loads are removed. In the full load departure condition, the oil and water tanks are full, the waste tanks are empty, and the cargo holds are full of seawater. In the full load arrival condition, the oil and water tanks are empty, the waste tanks are full, and the cargo holds are full of fish. Because the vessel uses a pressed cargo system, the cargo holds are always full when operating. To find the vessel's hydrostatics at different loading conditions, we completed a tank loading analysis using GHS, a general hydrostatics software. The analysis reported the vessel's weight, centers, and hydrostatics at each loading condition, as well as the righting arm curve. The displacement of the vessel must be low enough to meet the draft requirement. The weight at full load departure was originally estimated to be 1,184 tons. From the described analysis, the departure weight was reported to be slightly lower at 1,165 tons. The draft at this condition was 3.96 meters, which meets the 4-meter maximum draft requirement. Of the 3 conditions analyzed, the arrival condition was shown to be the most stable condition. The vessel's metacentric height varied slightly between each condition, and the GM was the highest for the arrival condition. With empty oil and freshwater tanks, there's less weight higher up, and because the cargo holds are full, there's a lot of weight lower down at the vessel at midships. These conditions lowered the vessel's vertical center of gravity and allowed for greater stability. The intact stability criteria the fishing vessel is required to meet are dictated by IMO IS 2008 regulations. These requirements show the minimum area under the righting arm curve for ranges of heel, as well as the minimum magnitude and location of the peak righting arm. The righting arm for the vessel's departure condition is shown on the right, and the vessel meets all the IMO requirements for each loading condition analyzed. I will now speak on the vessel's damage stability, which was evaluated using a 1-compartment deterministic damage stability analysis. The floatable length curves for the full load departure case are shown on the graph on the right. The triangular peaks on the graph are located halfway between each of the vessel's watertight bulkheads. The width of each triangular peak is the floatable length of each space. The blue and red curves on the graph are the floatable length curves, which represent the maximum flooding the compartments can hold before failure. The locations at which the floatable length curves and the peaks intersect is where the vessel fails stability. The FV Barramundi Atlantic's worst case for damage stability is when the aft machinery space is flooded at full load departure. In order to increase survivability in this condition, we would add bulkheads within the aft machinery space. The greater compartmentalization within the space would decrease floatable length and increase stability. I will now discuss our propulsion system, which consists of a main engine, a reduction gear, steering gear, and a bow thruster. The main engine we chose is a CAT 3512E diesel engine, which supports the 1,000 kilowatt load estimated to meet our propulsion needs. The main engine also meets EPA Tier 4 and IMO Tier 3 emissions requirements. The reduction gear has a speed reduction ratio of 5.5 to 1. The steering gear is a hydraulic wraps and slide type gear, and we included a hydraulic bow thruster for additional maneuverability. I will now discuss our electrical plant, which consists of 3 C32 marine generators manufactured by CAT, 2 of which are ship service diesel generators, and 1 of which is the emergency generator. Each generator is capable of supporting the estimated 500 kilowatt load needed for deck and auxiliary machinery, as well as house loads. These generators also meet EPA Tier 4 and IMO Tier 3 emissions requirements. There are a few areas of improvement for our design and deeper analyses to be delved into. For this reason, we have included a list of future work that could be completed. First, we would want to look further into reducing tonnage enough to bring back the deep frames into the cargo holds. We would also like to rearrange our tanks to fit within these deep frames. Also, we recognize that our generators are oversized, and in future iterations, we would choose smaller generators. We would also like to analyze our vessel's maneuverability in rough and calm conditions. Lastly, we would explore methods of making the trawling process more sustainable. One idea would be to develop a method of marine species rewilding. In conclusion, the FB Barramundi Atlantic is a concept design for a fishing trawler servicing the eastern seaboard of the United States. Much consideration was put into the arrangement of the vessel's deck gear, hull form, and machinery to meet the mission requirements. Thank you for listening to our presentation. I would now like to invite my group members and open up the room to any questions.
Well done, Steve. General question. You mentioned in your introduction this vessel is designed for fishing on the eastern seaboard. Are there any design concessions you have to make for our vessel meant for Atlantic waters versus Pacific Northwest?
The question was, did we have to make any design considerations between operating in the North Atlantic versus in the Pacific? Recognizing that we are a Class NK vessel, this was definitely a very large part in our design spiral. One of the key problems that this sort of interchange created was our spacing of our frames. In accordance with Class NK, frame spacing had to be far less than that in accordance with ABS or an American class society. And so because of that, there were more concessions involved with arranging our equipment.
One consideration that we did take into account for operating in the North Atlantic versus in somewhere like the Pacific Northwest was the general temperature of the water. One project we completed during this time was the design of a freshwater cooling system. And so the seawater temperature was taken into account there.
We also plan on completing an additional sea keeping analysis that takes into account the rough conditions of the North Atlantic waters.
So considering the background and the purpose of the Tesla as being the centerpiece of a reality TV show, I was just wondering, which is very creative, but how are you going to accommodate the extra POV, extra personnel for the TV crews and whatnot, and also how will you feed off the podcast?
The question was, as this vessel is designed in part for a reality TV show, how will we deal with any considerations that, change your typical vessel design, such as paparazzi? I guess I will begin by saying I think there is very little paparazzi in the North Atlantic, but they've got, I guess we have a mess and a TV and a coffee machine, so hopefully everybody is well accounted for.
Well, just as far as the TV crews that would be there and filming all the time, since it's a very small accommodation, or you can make people, kind of like double bunk and kind of sleep in shifts and that sort of thing.
We did not account for the TV crews. We were giving it a 9-crew complement requirement. Double bunking is illegal, so that will not be occurring. But we focused on the vessel's functionality and figured any reality TV incorporation they would have to.
Something to also add to that, during our initial research phase, there are actually quite a few videos of trawls being hauled up of that 27-degree ramp. And a lot of times those cameras are situated on a piece of, well, not deck machinery, but they're usually situated on deck somewhere. And a lot of times they're self-filmed.
I have a couple notes. First of all, nice presentation, excellent consideration for tonnage. Well done, well explained, nicely done. 2 questions. You have tier 4 engines on the boat. I'm glad that you guys realize the C-32s are a bit overkill. Good conclusion on your part. That is overkill. What considerations do you have for the equipment that's required to make those engines tier 4? Like selective catalytic reduction boxes and all that equipment, storage of depth, can take up a considerable volume. What have you addressed that in your design? Also, have you dealt with icing requirements?
The question was, have we considered the additional appendages or the additional machinery that may need to be installed for the engine that we have selected to meet tier 4 requirements? I would say that that is something that we would consider in our next round around the engineering spiral. We have left space open within our machinery space for said machinery, aft machinery space that is near our exhaust vents on the starboard side.
No icing considerations were taken into our stability at this time.
So maybe I misheard because I did get these questions for the weight estimate. You said there was a 10% margin and then you added a 10% margin for growth. Anyway, was that on top of the whole weight estimate or How did you, could you clarify your margin?
For our margins, we had a 10% acquisition margin so that as more weight was added to the vessel, possibly higher up in the vessel, that margin would be reduced as the weight of the vessel increased, while the overall estimate of the weight would remain the same. Whereas the service margin would be for maintenance.
I would also say that while we were completing our margins, this isn't necessarily directly related to that, but we did have a margin attached to our KG to adjust for during the ship's life, there will be an accumulation of items on the main deck.
Second question, what was your source of weight? Parametric.
The question was, what was the source for our weights? And it was a combination. We were using parametric analysis for a lot of the weights that we found difficult to sort of estimate. And then we also found our weights when we were sizing our different machinery. As we underwent this engineering spiral, one of the major projects that we had was to design our freshwater cooling system. And in a lot of cases, at the advice of our professor, we altered we took the base weight of that system and we set it proportional to other systems that would either be smaller or larger than that.
The methodology used to calculate a light ship weight estimate was outlined in ship design and construction.
And the use of deep frames to reduce your GRT. Are tonnage openings common in fishing boat design? It seems like it's contradictory because, with your volume the issue would dictate against having multiple tonnage openings. I'm just curious.
So our tonnage openings were recommended by our tonnage expert and were used in the superstructure to allow for progression through the space.
Is that common? Is that what it's defined?
We referenced the Aquama fishing vessel, which did use tonnage openings throughout their superstructure. I do believe it's a common practice.
We also situated those tonnage openings so that they were facing aft and they would be protected from prevailing seas forward.
Online, there's a question, just they were asking, what is the total main propulsion power? They wasn't sure if that was mentioned in the slides.
1,000 kilowatt load propulsion. Estimated to meet the propulsion needs.
Okay, thank you very much.